I've got a little scenario for you. Imagine that you're traveling on a really long flight across the country for business reasons, and let's just say that it's not going very well. You're in the middle seat, the person on your left reeks of cigarette smoke, and the person on your right has tried to start a conversation with you at least 5 times since you've boarded. Ugh. So, since you got nothing better to do for quite a while, you decide to record the plane's speed over the course of about 60 minutes to try and figure out how many rewards miles you might earn from this. And since you know that speed multiplied by time gets you distance, this is a pretty simple problem. The units of time will cancel out across the denominator in your multiplication, and what you're left with is how far you've traveled over that time frame. In fact, you'll also notice too that in a graph of velocity versus time, the distance that you've traveled is actually the area underneath that graph. Well, who am I kidding? This assumes a very perfect scenario. What happens if the plane hits a little bit of turbulence while you're recording? Or maybe your flight is just so bad that you started recording right at takeoff. That'd be like trying to find the area of a square, except the height of your square changes from left to right. That's impossible. Or is it? Instead of taking one measurement over the course of those 60 minutes, how about we take 2 measurements, or 3 measurements, or 100 measurements, however many we want. Therefore, the next logical step would be to take an infinite number of measurements. And thanks to calculus, that's possible. Now, I know that for some of you, when you hear the word calculus, you might have just a little bit of a panic attack, but I can tell you it's truly not that bad. I mean, I just barely survived it. Wait, what? To denote this action of infinitesimally sampling our data, we use what's called integration. First, we start with the integral sign, and then right in front of that, we write our function that models velocity. Then on the bottom side of the integral sign, we write our starting position on the x-axis, which is the time at which we started recording, and at the top we write our stopping position, the time at which we stopped recording. And then finally we multiply our function by the letters dx. And what this whole thing is going to do is it's going to divide the area underneath the graph into an infinite number of rectangles, add up the area of those rectangles, and return the area underneath the curve. To prove that this works, my neighbors and I outfitted a small remote control car with a DIY speedometer, put it on a treadmill, and took speed readings while we varied the speed of the treadmill. With our speed data, we created an algebraic function that best models the car's velocity during the experiment, and once we took the integral of that function over the testing window, we got a distance measurement that was within 10% of the distance reported by the treadmill. And that is just one basic example of the power of calculus. In fact, that's how scientists can calculate how much water has flown out of a lake based on river outflow data. Same goes for snowmelt data and even areas of climate science. So hopefully you learned something in this video. I know I had a lot of fun making it, and have an amazing day.